So today we're going to discuss 10.4 polar coordinates and the polar graphs. Previously, we have used regular angular coordinates all the time. You just use the coordinates x and y as shown on the right side on the graph. It's basically the um, you know direct distance to the x and y axis. So the coordinates of any point on a plane are defined, uh, distance, you know, to the x and y axis from the point, right? Um, so that's called the rectangular coordinate system, because when you draw those parallels as shown here, there are rectangular. Uh, all right, but we also have some other types of coordinate system. We have the polar coordinates we're going to discuss today, but we have some other types of coordinates, which we will probably not discuss in this course. So basically, for any point on a plane, we need two coordinates, uh, because a plane is two-dimensional. We can use x and y as we always did, but we can also use two other uh, coordinates. In polar coordinates, we use r and theta instead of x and y. And this r and theta are called directed distance and directed angle, and they have different uh, geometrical interpretation from the regular angular coordinates. So in this polar coordinates or polar coordinate system, we have just like the origin in the rectangular coordinates. We call it pole instead of the origin, but they play in the same role. And then we have the polar axis, and the polar axis is just the positive x-axis, so it's half of the x-axis. It starts from the pole and pointing to the right. And then for any point P, okay, so we are on the same plane, but we use different coordinate systems. Okay, the point we're talking about P is the same. And then what you do is you're going to uh, measure the distance between the pole and the point P we want to locate. And we call that R. Okay, and we call it direct distance because R can be defined negative as we're going to talk about later. So it's not just distance; it has some direction. And also the other variable we use is the theta. We 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 call it polar angle. And the polar angle theta has some direction also, so it's already directed. So it's called directed angle. Uh, so what you do, you start from the polar axis, you rotate some angle to get point P as shown in the graph, right? And this angle is the theta. When you rotate uh, counterclockwise from the polar axis to reach P, then we define this theta positive. And if the the point P is under the polar axis, then you have to rotate clockwise to reach P, and that in that case the polar angle. So this is the same uh, sense of rotation we you learned in trigonometry, okay, for the positive and negative angles. Remember, uh, clockwise rotation that be negative angles. I counterclockwise rotation for an angle will be positive, right? Okay, so one of the huge differences between the polar coordinates and the rectangular coordinates is the polar coordinates are not unique. That is because we are using, especially using the polar angle theta, and you know, and if you rotate a whole cycle, uh, then you come back to the same point P, right? So, and you either increase a angle of 360 degrees or 2 pi in radians, or negative 360 degrees, or you can actually rotate the multiple circles or cycles, and then you will have different values for the angle of theta. All right, that's essentially because of the uh, periodic nature of the polar angle. But that's not only the reason. Another reason, because we can also define the or direct distance to be negative, not just positive, but it can also be negative. In that case, then we can have the different representations with the polar coordinates for the same point on a plane. In other words, for any particular point on the polar plane, you can have different coordinates. Okay, and one of the spatial point on the polar plane is the pole. Um, you know, this is a spatial point because the polar angle for the pole itself, okay, the pole, we're talking about the point in here, is undefined. The pole itself has the directed distance r equal to 0 because r is the distance or directed distance between the pole and the point P. But if P is the same as the pole itself, then r will be equal to 0, and then you you have nowhere to uniquely define the theta, because it really doesn't matter what theta is. As long as r equal to 0, it's the same point pole. Okay, so the pole has some ambiguity that the polar angle theta is arbitrary. Okay. Okay, so as I said before, both R can be positive or negative. But in many cases, we usually use the positive values for the R. But for the polar angle theta, we can use both positive or negative. And sometimes it's even more convenient to use negative angles. All right, just keep in mind as you did in trig. Okay. Any questions about this? So we are talking about a totally different coordinate system, but on the same plane. So we want to describe the plane with another set of numbers, or on theta, the directed distance and the directed angle in state of xy. All right. Okay, let's just look at several examples about the polar coordinates of some points, special points on the plane. Okay, so the first thing is if you talk about the positive x-axis, for xy coordinates, or the rectangular coordinates, or all the points on the polar axis, then the theta will be 0, obviously, because all the angles are measured from the polar axis, right? So all the points on the polar axis will have theta equal to 0. All right. But then how about the positive y-axis? And that'd be theta equal to power of 2 or 90 degrees, because if you rotate 90 degrees from the polar axis, right? And then if you rotate another 90 degrees or power 2, and then you're going to get the opposite direction from the polar axis. And that's the negative x-axis, or negative half x-axis in the rectangular coordinates. And obviously in this case theta will be pi. Okay, so for any point on the opposite direction of the polar axis, the coordinate theta will be equal to pi. And then if you further rotate 90 degrees more, then you go down to the negative y-axis, or negative half y-axis, and then any points on the negative y half axis will have pi equal to 3 pi over 2, theta equal to pi over 3 pi over 2. I don't know why I put pi over 2. It should be 3 pi over 2. Need to correct it. Okay, so these are the four spatial directions. Okay, so let's just look at some spatial points on the plane. The point of 3 pi over 4. So now you should consider the polar coordinates instead of the rectangular coordinates. So 3 will be the distance between the point to the pole. Okay, and pi over 4 is the angle. You know, you rotate starting from the polar axis to the point. So this case is 45 degrees, so that's pi over 4 in radians. Remember how to convert between radians and the degrees. All right. Okay. So if I reflect this point across the origin or the pole, then we get another point in the third quadrant in the XY coordinate, rectangular coordinate system. And then, you know, you can think of this in two different ways. You can think of it as a reflection of the point in the first quadrant to the third quadrant. In that case, you just change the sign of the R value to -3, and the angle theta is still powerful because the operation here is just to reflect the point, and that only changes the R value to negative. Okay. So if you think, when you reflect across the origin in rectangular coordinates, that R becomes negative, okay? But if you think of this point in the third quadrant as coming from a rotation of the original point in the first quadrant by 100 degrees, 180 degrees, right? You can rotate this point in the first quadrant 180 degrees and get the point on the third quadrant. You get the same point in the third quadrant, right? And in this case, you don't change the value for R. It's still 3, but you do add pi or 100 degrees to pi over 4. So pi plus pi over 4, that's 5 pi over 4. So this point can be either represented by -3 pi over 4 or 3 5 pi over 4. So they indicate the same point on the plane. All right. Okay, another example is the point of in the fourth quadrant. So in this case, the distance from the point to the pole is 4. But the angle here is negative with 4 degrees, so negative power 4, because you rotate it clockwise from the polar axis to get this point. So the angle is negative. But if you think you start from the polar axis and you rotate the 7 power 4 counterclockwise, okay, you rotate a point on the polar axis with the same length or distance from the pole, you rotate it through the first quadrant, then go to the second quadrant, and then go to the third quadrant, and then finally you reach the point in the fourth quadrant. Then the angle you rotated is 7 power 4. Okay, and then in that case you don't change the r. Okay, you only change the angle theta to 7 power 4. So the point can be represented either by 4 negative power 4 or 4 7 power 4. So you can see any point on the polar plane has multiple representations. The coordinates of polar plane are not unique, in other words. Okay, any questions? So just make sure you understand this polar coordinate system. It's totally different from the rectangular coordinate systems. Okay, but then one of the reasons or questions is, why do we need these polar coordinates? The reason is, it is not always the most convenient way to describe the curves or geometry on a plane by rectangular coordinates. It is much more convenient to describe circular shapes by using polar coordinates, as you will see later a little bit. Any questions about these examples? No question, then I'm going to go to the next page. Okay, so then we have two types of coordinate systems on the same plane. Then obviously, they should have some conversion between those two coordinates systems. In other words, if I give you the rectangular coordinates, you should be able to find the polar coordinates of the point on the plane. And if I give you the polar coordinates of the point on the plane, then you should be able to find the rectangular coordinates of the same point. Okay, because we got the same point on the plane, but we use different representations, right? So let's talk about coordinate conversion. Okay, and then there are two ways for the conversion. You can convert from polar coordinates to the rectangular coordinates, or you can convert from rectangular coordinates to polar coordinates, and the formulas are listed in here. Okay, so for example, from polar coordinates to rectangular coordinates, you just use the formula x equal to r times cosine theta and y equal to r times sine theta. So you can see from the graph in here, r is the direct distance and theta is the direct angle. And you look at the right triangle in here on the lower half plane in the first quadrant, then cosine theta is defined as x over r, right? If you still remember the trig functions, so that means x equal to r cosine theta, and the sine theta is defined as y over r, right? So y equal to r times sine theta. Okay, and you can also use the Pythagorean theorem to convert from rectangular coordinates to the polar coordinates. So if you are given rectangular coordinates x and y, then you can easily find the r by taking the sum of this x squared and y squared and take the root. right? Or you can simply use the distance formula from the origin to the point x, y. The distance r is just the square root of x squared plus y squared because we uh, usually use the positive value for r, right? And also, tangent theta is defined as defined as a y over x in the trig function. So then you can determine r and theta from x to y in this way. So this is the conversion between the two coordinate systems. All right. Uh, okay, let's just do some simple examples. Uh, for example, how do we convert the polar coordinates 4 pi over 2 to regular angular coordinates? So obviously 4 pi over 2 are polar coordinates in here. So r equal to 4 and theta equal to pi over 2. So we just use the formula x equal to r times cosine theta to get the x coordinate in the regular angular coordinates. So so r cosine theta, so that's just 4 times cosine pi over 2, and we know cosine pi over 2 is 0. So 4 times 0 is 0. So x equal to 0 in here, and the y equal to r times sine theta. So that's 4 times sine pi over 2, and we know sine pi over 2 is 1, so we get 4 times 1 equal to 4. So the regular angular coordinates for the point is 0, 4. So you can easily see that's actually the case. And that's the point on the upper half y-axis. Is 4 from the origin, right? So r equal to 4 and theta equal to power 2. Okay, and this can be easily read from the graph that the x coordinate is 0 and the y coordinate is 4 also. All right, so that's pretty straight. Okay, now let's talk about another example. We want to convert the regular angular coordinates 0, -5 to polar coordinates. So this time we need to do it in the reverse way, the reverse. So the rectangular coordinates are 0 and 5. So x equal to 0, y equal to -5. So we just use the formula r equal to square root of x squared plus y squared. So you get a 0 squared plus -5 squared inside the radical. Obviously, you get the 0 squared equal to 0 and -5 squared equal to 25. So you add them, you get 25, and take the root, you get 5. So r equal to 5. And you easily draw the point on the rectangular coordinate. So that's a point on the negative y-axis, right? 0, -5. So that's down 5 from the origin. It's on the negative y-axis. So this time the angle theta is just 3 pi over 2, 270 degrees. Okay. So that's how you convert from between those two coordinate systems. So it is usually convenient to draw the graphs for those spatial points. Okay, instead of just using the formulas. Any questions now? No question. Then let's just go to the another problem. Okay, so let's just convert the regular angular coordinates 3 and negative square root 3 to polar coordinates. So again, the regular angular coordinates are given. So x equal to 3, y equal negative root 3. So again, just to use the formula r equal to square root of x squared plus y squared. So we get a 3 squared plus negative root 3 squared. 3 squared is 9, and negative root 3 squared. So, first, you don't have to worry about negative sign because when you square it, it becomes positive. So, so basically, it's the same as square root 3 squared. But, when you square a square root, you get the number inside the radical, right? So that's just 3. So 9 plus 3, that's 12. And you can rewrite that 12 as 4 times 3 and take the root of 4, you get 2. So then you have 2 in outside of the radical and times root 3. Okay? So that's all. And for the theta, we can use the formula tangent theta equal to y over x. So that's negative root 3 over 3, and you get theta equal to 11 pi over 6. Or you can write as negative pi over 6. Okay. So we do use the formula tangent theta equal to y over x in here to figure out the angle, but you don't have to use the always like the previous example. When the points are on the x or y axis, you can just read it directly from the graph. Okay, and that also avoids the problem of dividing by 0. In this case, if you use the formula tangent theta equal to y over x, you get a negative 5 over 0, and that's undefined. So it is more convenient to read the angle theta, polar angle theta from the graph directly instead of do a calculation. All right. So that's the other example. Okay. Okay. Let's talk about some interesting thing now. How to use polar coordinates to describe curves or lines. Okay, let's just do some simple examples. Let's say we want to graph the polar equation r equal to 2. Okay, so first you have to be careful about this because we are talking about the polar coordinates. So it's r equal to 2. So that's not anything like x equal to 2 or y equal to 2. It's r equal to 2. We consider the curve in polar coordinates. So you can consider it as a different plane. All right. So what is the what locus of this equation describe? Okay. In other words, what is the set of the points described by the equation r equal to 2 in the polar plane? If you think about r, it's just the distance between the pole to the points on the curve. Okay, so r equal to 2 is a curve. Okay, just keep in mind. Then this polar equation r equal to 2 is actually all the points with the same distance 2 from the pole. So that's just the circle with radius 2 centered at the pole, right? So you can see you can use a really easy way to describe a circle in polar coordinates. How about the polar equation theta equal to 5 pi over 6? So how do we graph this equation? So what it means is all the points with the polar angle 5 pi over 6. And that's actually the line with polar angle 5 pi over 6 and passing through the pole. Okay. And then that line can be divided or split into two parts. One on the upper and the other the lower part. Okay. And for the upper part, you have the direct distance r to be positive. For the other part below the polar axis, the r will be negative because you reflect the upper half to the lower half across the pole, right? So this equation theta equal to 5 pi over 2 does describe the whole line with the polar angle 5 pi over 6 passing through the pole. Okay, let's show in the graph. How about the polar equation r equal to 2 secant theta? Okay, it might be a little hard to see from the equation itself from the original form. So why don't we just convert this equation into rectangular coordinates? Okay, first, why don't we just rewrite the secant theta as 1 over cosine theta? So we get the r equal to 2 times 1 over cosine theta. And then we multiply cosine theta on both sides. So we get r equal to cosine theta equal to 2. But if you still remember the conversion between the two types of coordinates, r times cosine theta is just x. So the equation is actually x equal to 2 in the rectangular coordinates. So this is a vertical line passing through a 2 on the polar axis. So you can see, the equation of a line, okay, actually becomes more complicated in the polar equation, and that's very understandable because polar coordinates are more convenient for polar or circular shapes instead of lines. So we usually use rectangular coordinates for the lines. Okay. Any questions at this point? No question. Let's just do. Okay. Okay. Let's talk about slope and tangent lines. How do we describe the slope of tangent line as shown in the graph? So there is a curve on the polar plane as shown in the graph on the right, in red, and then we get the point on the curve, and then just draw tangent line there. So the point on the curve is r theta with the polar coordinates r theta. And then how do you find the slope of tangent line to the curve at that point? And given the equation for the curve, r equal to f theta be a polar curve. Okay, let r equal to f of theta be a polar curve. So r equal to f of theta is just a curve in the polar plane. Remember, we should use the language of r and theta instead of x and y. So any polar curve will be r equal to f of theta instead of y equal to f of x. Okay. So we want to find the slope of tangent lines to the curve. Okay, any point on the curve, the tangent lines. But we don't have any formula for the polar coordinates for the tangent lines. But we can convert this problem back in the rectangular coordinate system, and then use the formula. We are familiar to do the problem. Okay, so first we need to rewrite, or convert these coordinates into rectangular coordinates. So just use the formula of the conversion: x equal to r cosine theta and y equal to r sine theta. But r is f theta. We're talking about the curve, so on the curve, r is same as f theta, right? So we got the f theta times cosine theta for x and the f theta times sine theta for y. Okay. So this is actually the parametric equations. Okay. So the parameter here is theta, right? So for any point on the curve, we got the x equal to f theta times cosine theta, y equal to f theta times sine theta. Okay. Then we can use the formula we had before for the parametric equations to find the value of dy over dx, or the slope of tangent line. That's always the case. The slope of tangent line to a curve is always dy over dx if we consider the problem in the rectangular coordinates, right? Or in the rectangular coordinate system. Okay, so then what you do is just take a derivative of y with respect to theta divided by the derivative of x the derivative of x with respect to theta also, because in this case x and y are both functions of theta, the parameter. Okay, if you review that part we did before for parametric equations. And then you can use y equal to f theta, y equal to f theta times sine theta, x f theta cosine theta to find the answer. So take the derivative of theta of f theta and sine theta with respect to theta by using the product rule, because you got f theta times cosine theta. So we got the f theta times cosine theta plus f prime theta times sine theta on the top, and then negative f theta sine theta plus f prime theta cosine theta at the bottom, because you just use the product rule here. And we know the derivative of sine theta is cosine theta, and we know the derivative of cosine theta is negative sine theta. And then for the other thing, we just take the derivative of f, so that's f prime theta, and keep the other part, sine theta or cosine theta, unchanged. So that's how you find the slope of tangent line. Okay, so especially when there's a horizontal tangent line, then dy over d theta will be 0, but dx over d theta is not 0. Then if you divide those two things, divide with d theta divided by dx over d theta is 0. So that essentially means dy over dx is 0. That's the horizontal tangent, right? But when dy over d theta is not 0, but dx over d theta is 0, then we get the 0 in the denominator when we compute dy over dx. But it's not 0 in the numerator, so we got the something divided by 0, and that's undefined. And in that case, we actually got the vertical tangent, right? So we still have one page to do, one slide to do in this section. And, we're going to finish it on Thursday. All right. Any questions? So we just have one more example to do in this section. So let me just stop recording.